What's up, everybody? It's Mike from A3Academy, and today we're going to be talking about simple pendulums and how they relate to simple harmonic motion. So let's get started. Here we have a pendulum, which consists of a small object, or what we call the pendulum bob, suspended at the end of a lightweight cord. Now we have to assume that the cord does not stretch, and also that its mass can be ignored relative to the mass of the bob. So what happens when we set this pendulum in motion is that it oscillates along the arc of a circle, and it has equal amplitude on either side, and basically it undergoes simple harmonic motion. If we look at the position of the pendulum at the top of the swing, we can calculate the displacement. So here we have the formula, x equals L times theta, where x is the displacement along the arc of the circle, L is the length of the cord, and theta is the angle the pendulum makes with the equilibrium position. We can also say that if the bob has a mass of m, that the restoring force, which is the force acting on the bob to bring it back to equilibrium position, the force is equal to negative mg sine theta, where g is the acceleration due to gravity. What this tells us is that the force, the restoring force, is proportional to the sine of the angle, not to the angle itself. But for motion to be truly simple harmonic motion, the restoring force actually has to be proportional to the displacement, or in this case to the angle. However, we do know that for very small angles, that's about 15 degrees or less, sine of theta is almost identical to theta itself. You can check this on your calculator or with a table. For pretty small angles, those two values are nearly identical. So we can say that F equals negative mg theta when the oscillation is very small, or the displacement of the pendulum is small. And substituting in the first equation, we get that F equals negative mg over L times x. The reason this is important is it gives us the restoring force in the form of F equals negative kx. In this case, k is mg over L. So since we have it in this form, which is also known as Hooke's law, the motion is truly simple harmonic. We can use this value of k and substitute it into the equation for a simple harmonic oscillator, which we have in the previous video. If you haven't watched that, you should check it out now. But substituting into that equation, we get that the period of a simple pendulum is equal to 2 pi times the square root of L over g. And since we know that the frequency is equal to 1 over t, we can also say that the frequency is 1 over 2 pi times the square root of g over L. Now, one interesting thing about these two equations is that nowhere do you see m. And that tells us that neither the period nor the frequency of a simple pendulum depend on the mass of the bob. This might be a little bit counterintuitive, but if you've ever pushed, let's say, a small child and an adult on two swings at once, you probably noticed that they swing with the same frequency, so they can match up their swings. And while this seems strange, it is true for simple pendulums undergoing simple harmonic motion. All right, let's look at an example. So we have a geologist who performs an experiment with a simple pendulum that has a length of 27.5 centimeters. And he finds that the frequency is 0.948 hertz. So we want to find the acceleration due to gravity at this location. This is a pretty simple problem. All we need to use is the formula for the frequency, but we need to rearrange it to solve for g. So we just square both sides and isolate g, and we get that g equals 2 pi f whole squared times L. And we can substitute the values now. We have the frequency, which is 0.948 hertz, and we also have the length of the cord, which is 27.5 centimeters. However, we need to remember that g is in the units of meters per second squared, so we have to convert those centimeters into meters to get 0.275. Now, typing this into a calculator and solving, we get that the acceleration due to gravity is equal to 9.76 meters per second squared. Since this is less than 9.8, which is the accepted value, we know that the geologist is above sea level. And if you want to find out exactly how high he is, you can go watch the Intro to Gravity video, which will let you calculate exactly the height above sea level. That's pretty much all you need to know about simple pendulums. I'm Mike from A3 Academy, and as always, the more you know, the better you are.